In a previous video, I said a lot of things and I didn't do them. In this video, I'm going to catch up on some of the tasks that I said I was going to do for my one viewer or stalker neighbors. So starting off with one thing I said, so I was going to talk about the homotopy. So if we're going to talk about homotopy, start with the first sentence, right? In the mathematical field of algebraic topology, the homotopy groups of spheres describes how spheres of various dimensions can wrap around each other. This whole video, just gonna show the case of wrap around each other and the other case, not wrap around each other. And as of, like most math, we'll start with the not, all right? So, here it is. Just the basic, here we're going to use the exponential again, okay? What is this entire GeoGebra app? 7 lines. All right. So why we're going to talk about the homotopy of spheres is right here. These two reasons right here. But there's some nuance first. Starting with the nuance. Could make a slider like that. Oh, I don't know. Call it P. Okay. Unit parameterization of a unit circle, right? So 1 minus P squared over 1 plus P squared. That's going to be our X value. Y value, just 2P over the same, right? It's really just originally comes from a triangle. This is the Pythagorean theorem with some algebra done on it. That's all it is. Okay, so now we have 2 points, A and B. Here, let's rename that. You see settings. Put it, say A and B. So, go unit circle. With this is how we talk about nuance. Just make another slider. Call it M for multiplier. All right. So this P here. Ooh. P. Notice the limits of P. Let me just change the limits here to 5M. Okay, now that M is on 1, really nothing should have changed. Okay, to avoid doing this, we could find its locus using the locus tool. I want the locus of the unit circle as a function of our parameter. See here, currently, with P set to 5 and -5, that's the limit of the circle that can be drawn. By decreasing the multiplier, we could see less of the circle can be drawn, or increasing, and of course we could finally get to the limit if need. Another geometric interpretation of this same idea. So point there, call that one T sub 1. We could change its definition. Yeah, P sub 1. Its X value will always be 0, and the parameter will be P. This is the unit parameterization of the unit circle geometrically, while the line on the unit circle, the point on the unit circle moves around the unit circle as P varies. It can also be interpreted as P is also a line moving up and down the y-axis. So, within graphical algebra packages, there are limitations. And I guess those limitations is what I'm calling a nuance. This is a demonstration of one of those nuance. With that, back to homotopy. So, as I said before, basic construction of all the cyclic harmonics can be given, right, in this, well, almost all can be given in this form, like this. So, and notice, to notice what I noticed. So as A varies, right, without even moving P, our point Z1 moves. So, same thing with B, right? Even without moving P, our Z1 will move. So that is, we can find the locus. So as A varies, what is the locus of our complex point? It is this sphere right here. And how does it behave as we vary A? Oh, we can see it follows along that circle. How does A behave when we vary B? Vary P, and there it is. The whole reason for the first few minutes of rambling, this wrap around each other. This has to be one of the best examples of demonstrating how this idea, this abstract idea of wrapping around. Notice here I have made the loci from dotted lines, right? But what's great about these lines in GeoGebra, okay, as maybe this circle wraps around itself, it's still trying to create a dashed line, but because it's at a different frequency, the dashes run into each other, demonstrating this idea of wrapping around. So with that, notice now going a little slower, okay, A is actually really moving too serious. Let's turn this off. All right. Every cyclic harmonic curve, by definition, right, can be shown, right, with this function for what's going on behind the scenes. We're really taking two osculating circles, right, and using the point. Okay, see there? Good. Now, to make them wrap around each other. There it is. See, almost, you say, hey, you say, oh, they're going in a circle around. No. Notice by the time I get to 2 pi, where have the dashed lines gone? They're still there. They've just wrapped on top of each other. You can slowly see it happening. And I do hope for many that this is enough proof of the true power of graphical algebra programs. With that, I thank you. I will put this up on GeoGebra, same as the channel name .vcross. And I guess I'll make a promise for the next one. It's the channel name. Sure, dot and cross are vector operations. I try and just give a new example of the dot product. Not the standard, oh, it's the video game reference. There's many examples used. I try and come up with a unique one, and I thank you.